Hello, Fun Nation. My name is James, checking in here with team number 2337, the EngiNERDs, here at the First in Michigan Livonia District event. The EngiNERDs have a really awesome robot this year. There's so much to learn about here. Already won the category number 2 district event. So much to learn for first teams in this robot. Here to talk more, I have Claudia, Andrew, Alex, and Owen. Let's find out more on Behind the Bumpers. All right, Claudia, can you tell us a little bit more about the end effector and pretty unique mechanism here for the EngiNERDs?
Yeah, all right. So first of all, in the beginning of the year, we sort of wanted to figure out what we wanted to do, what game pieces we wanted to focus on. And so for our end effector here, we wanted to focus on coral. So the path of the coral, it enters through here from the coral station. This funnel here gives us a greater room for error in case the coral's messed up or our positioning is a little weird. So the coral comes in here. This is actually at a 55-degree angle compared to the end effector, which is at a 45-degree angle. And then it travels through here, these wheels spin, and then we're able to spit the coral out onto whatever level we want to spit it out onto. These gray wheels here are meant to de-score algae. So basically, during a match, if we need to score on L3 or L2, we need to get rid of that algae. So we bring the arm forward, kick it off, run those wheels, and that algae just gets kicked out of there so we're able to score on those levels.
Claudia, clearly a well-engineered design here. Can you tell me a little bit more about the prototyping process and some of the design iterations you have here?
Yeah, so basically we wanted to sort of think about what we wanted to do instead of how we wanted to do it. So in the beginning we were like, oh, we want to intake coral, we want to score coral. Then we started figuring out the mechanisms for how we wanted to do that. At first we had wheels set up like an axles down here, like rows of axles here. And then we had the coral running through here. And then later on, we found out that instead of having 2 motors running 2 different rows of axles, we could just have 1 row of axles and lessen our weight by just having these hex shafts down here that let the coral slide right on down.
Very cool. Thank you, Claudia. All right, handing it over now to Andrew. Can you tell us a little bit more about this pretty unique arm and elevator mechanism you have here?
Yeah, sure thing. Once we knew where we wanted coral to go, it was my job to kind of get it where it needs to be in the fastest time possible. So the way we decided to do that was with a rotating arm right here on a virtual 4-bar that would keep Claudia's section parallel to a certain angle. During the prototyping phase, we had calculated and tested the optimal angle to score at. So once we knew that in CAD, we had prototyped a very simple arm with a fixed belt drive down there, which would rotate this section up here. So that way, no matter where we drive, it is the perfect angle to score. Right now, that's about 45 from horizontal. And we decided that we would package this all on a 2-stage elevator. We did this by putting the entire arm right here in a 3.5-inch tube. If you come through the back here, you'll see a Kraken sandwiched right in the center of the tube right here. So that Kraken is powering a 125-to-1 gear, a planetary gearbox, which drives this about 18-inch arm pretty fast. We can go from horizontal to vertical in a fraction of a second. It's a very quick design with a lot of torque. And yeah, I mean, it's fast. We wanted to make sure that the arm and elevator combo could get to L1 and L4 with the same exact the same design. And for repeatability, we put a Lamprey absolute encoder right behind that plate right there. So when we start each match, we know exactly where the arm is, and then with the string pipe here, we know exactly what height the arm is. So we're a very repeatably quick scoring design here.
And that's evident in your performance, Andrew. Clearly a well-engineered design, so thank you so much.
Yeah.
Owen, can you tell me a little bit more about the climber? I understand that you've improved it now for this competition. Can you tell me a little bit more about that?
Yeah, I would love to. So actually our climber, here, I'll explain the climber. So this foot right here, what happens is we've set this arm all the way down. This in turn then pushes what we've been calling the foot down, And then once our climber or the cage gets lodged right here, we pull this arm back, and at some point it gets lodged into the center of our robot. This arm would be more down here, and then the cage would lodge right here. And as we pull this arm back, it goes slowly and slowly more into our robot, which in turn puts it in like the center of gravity of our robot, which lifts up our robot intentionally with it. And then at last competition, you were talking about our performance at Kettering. So we had a big problem with like centering the cage and getting it to work properly. So what we in turn do is we cut Lexa in panels, in which it hits the panels, it centers it, it locks straight onto the foot, and then you pull it up, it climbs right there, right and done. Now the cool thing about this elevator is it also doubles as our algae intake. So we found that the way that, also, quick side note, the way this foot works is it hits this hex shaft and it just clamps onto it, and the way that we put it back is by pushing the hex shaft back and then pulling the foot with it. So there's a little clip that goes into the hex shaft right under here, and once you push it down, it goes into the hex, like right underneath it. So the way that we put it back is we push this forward, push it forward, give it a second. There we go. There it goes, and then it comes back up. So, and this also doubles as our algae intake. So the compression from this bar to our bumper is the perfect start with it. And then the panels that we cut to help center the elevator is perfect for trying to keep the algae within our robot. So if we just run it pretty well. We ended up having to chain it because we started stripping some pulleys and some belts on this side. But as we run this, it gets caught right here. Well, it would be down. It gets caught right here. We can do it. Then we can spin it out just right there.
Wonderful. Thank you, Owen.
Yeah,
I really
of course.
appreciate that explanation. Now, Alex, I'd like to talk a little bit more about some of your programming features on this robot. Heard you have like an auto drive feature, so maybe let's take a look at what that looks like for the nerds.
Yeah, I guess I'll start here with our two limelights here on the robot. We've got one down here for the reef, and that allows us to localize the tags that are right there, right in front of your face. Then we've got one right up here for the coral station, so that way we can line up properly, so that way the human players have a nice, consistent, easy load into our robot. Then for our auto drive sequence, how we managed to do that was we used the CTRE swerve generator, then from there use their field-centric facing angle method. So then we broke it up into 3 separate steps. The actual driving to the point using our PID controllers for the X and the Y direction. Then we set a target position, and then we set an approach position. So when actually driving to the point, we'll just take a look at we'll basically simulate a joystick of your controller, and then we'll figure out the angle that should go at and the power you should be sending it. Then that's how we're able to actually follow to a point. We'll take a look at the X and the Y direction. Then for the target position, we have set constants off of the April tags because we noticed the symmetry between the different sides of the reef. They should all be the same. So we just take the April tag as the center, and then we work our way off from there. And that allowed for a lot of repeatability. But then we noticed that whenever we went to the back side, we would slam into the reef. There was different points where we didn't see the April tag quick enough, and we went to the wrong position. So then the third point is setting the approach position. What we do for that is we scale it based off how far away we are, and then we bring the set point back. So when we're setting to the far side, we'll go all the way towards that intake wall, and then we'll bring the point in as we come around. So that allows the robot to have a nice arc as it goes through the angles, and we're able to automatically drive between all the different positions.
Wow, Alex, thank you so much for the explanation. And EngiNERDs, thank you so much for taking the time to talk with us today. Incredible robot this year, currently ranked #1, I believe, at the Livonia District event. Best of luck throughout this event and the rest of the REEFSCAPE season. My name is James with Fun Robotics Network. Thank you so much for watching.